So my name is Seun, and I'm the founder of Polytop Labs. We're like a core team for Polkadot. Describing our implementation of zkCasper, which is a succinct and accountable light client protocol for Casper FFG. So I guess the first question would be, why not just use the so-called sync committee if you're familiar with the Ethereum consensus protocol? A few issues. The sync committee cannot be slashed. I mean, today anyways. And in our opinion, this violates the safety guarantees of any sort of proof of stake protocol. If you recall, sort of the safety guarantees of a proof of stake protocol is predicated on the ability to be slashed if you try to double vote or double sign, equivocation, all these different words for the same thing. Also, even if they could be slashed, this amount at stake is just so low, it's basically pointless. I mean, you have like, what, 27K ETH, around 30 million. Say I had a bridge that had over 100 million locked, secured by the signatures of this sync committee. It's a very profitable hack, in my opinion. And even more so, we're seeing the rise of MEV and sort of MEV use cases. I think one of the most important MEV use cases would be for actually node collusion. So you can imagine I'm running MEV boost, and it says, look, if anyone who's also running MEV boost is also in the sync committee and there's a supermajority set, then I want all of us to fork and sign this fake chain where we just basically withdraw all the funds on any bridges that are dependent on our signatures. So yeah, I write more, of course, about this more extensively in the our official research blog. And so given all these problems, we've decided to tackle just verifying the Casper FFG consensus proofs directly. Just a fun meme, because I think it was Barbenheimer during the time. Of course, building a sync committee light client is pretty easy, but when you start looking at Casper FFG, you're dealing with, what, 850K validator sets size. It's a bit much. So let's just quickly review Casper FFG. Currently, I think on the Beacon Chain website, you can find that there's like 800K validators actively validating the chain, even though there's only like 10K nodes. So it's just like multiple nodes, or there's multiple keys per node, something going on there. But it will degrade the network to sort of pass around a single consensus message, you know, sort of round robin fashion, and we just add our signature to that. That doesn't scale. And so what you have is the protocol splits up all the entire set into this attestation committees. Max size for the attestation committee is about 2,048, so you would probably have like 500 attestation committees at any point in time. And each attestation committee just basically signs this attestation message with their own BLS key. It's the case that every attestation committee has a different message to sign, because they also sign what is the committee index, so no two messages will be the same, so you kind of also aggregate that as well. But of course, because they're using BLS, it's the case that the signatures can be aggregated as well as the public keys. But you know, if we just aggregated the signatures, aggregated the public keys, we don't actually know who are the constituent public keys in the aggregate, so we don't have accountability. So you can't just do this naively on chain. So we'll just look at more of the implementation details of Casper FFG. The protocol tracks all of the validators in the so-called validator registry, and it's the case that validators are never removed from this registry. Once you're added, you're there forever. And if you maybe exit the queue or you get slashed, you just have your metadata updated that says you're no longer a part of the set. And of course, new validators just keep getting added to the set, and that list just grows on indefinitely. Hopefully that gets bounded at some point with, of course, single slot finality on the horizon. Now, this registry is also an SSZ object. For those of us who are familiar with the consensus specs, it's just a new way to store data that preserves the ability to Merkleize this data. So it's the case that we can always get Merkle proofs for any validator in the set. This will be important later on, but the last thing I'll note on Casper FFG is that the Casper FFG vote is this so-called tuple of epoch boundaries, so the so-called source and the target epoch boundaries. And a more visual explanation for this would be to see this. Let's say this is the genesis that's sort of finalized by the protocol implicitly. This would be finalized, this would be justified, well, and then I guess, well, this would be justified, this would be finalized, and this would be finalized, and then of course the blocks, they grow from that point on. All right, so a refresher on BLS, just before we start diving deep into the protocol itself. BLS says, hey, look, if you have some signatures, it's the case that they are aggregatable. Just take elliptic curve point addition. And it's the same thing for the public keys, right? You can aggregate the public keys, and then you just do a single parent check, and that will verify all these signatures in a single parent check. Of course, this is the case that your public keys have all signed a single message. If you have distinct messages, then it's the case you have to take a sum of the pairings. This is classic, same thing going on here. But in a more advanced case, you now have what are multi-signatures. So this is actually an already aggregated public key, and you have already aggregated signatures, and then you're still sort of summing that up. And they're all signing over distinct messages, but you can still verify the signatures in this way. So you can imagine this aggregated public key are the sort of committee public keys. The signatures are signing over their own attestation messages, and this is kind of how we would verify these signatures. You could also do this in a SNARK, although I don't know how feasible that would be, because that would be close to like 1,000 pairings in a single SNARK. Hopefully folding helps there a bit. So take a step back. The most expensive part in Casper FFG is actually in handling the public keys. You have like, 800K public keys to verify. The verifier has to be aware of these public keys just because of how BLS works. You would have to take the sum of those public keys if you wanted to amortize the costs of the attestation message to a single pairing. But yeah, what if we could introduce a SNARK proof that sort of attests to the validity, in quotes, of the aggregate public key, that says, hey, look, all of the constituent public keys of this aggregate was correctly computed from a set the verifier knows. So in the scheme, the verifier just only knows a commitment to all of the validators in the validator registry, and they are presented with the aggregated public keys of each attestation committee and a sort of bit list that says, look, all of these public keys correspond to these bit lists, these positions in the registry. We need the bit list for accountability, otherwise we don't know who signed in the committee, and it's the case that, well, we can't slash people if they double sign, which goes back to the problem the sync committee had. So I won't get too technical about the APK proof schemes. Actually, this is work done by Web3 Foundation researchers, and it's the case that Alistair already presented the scheme himself at a previous edition of ZK Summit, but I'll just summarize what's going on there. The scheme is built over, the so-called half cycles of elliptic curves, in the sense that you can embed what is the base field of a curve into the scalar field of another curve. This is useful in SNARK recursion and all that fun stuff. But in this case, we're just dealing with points that describe public keys, which are elliptic curve points themselves. And we embed those points inside of the scalar field of another curve, and then we can start to do commitments in that curve and opening proofs and classic SNARK stuff. So the next thing is we're basically doing elliptic curve point affine addition. Now we use affine because other coordinate systems would have 3 points, and then we now have more than 2 commitments that we have to open. The less commitments to open, the better. And it also supports representing the field elements or the bit list as either a field element or in the binary representation of the field elements, which uses a more complicated polynomial commitment, but that's I won't get into that as well. Also, the SNARK scheme doesn't do permutation checks, so there's no wiring whatsoever. We maintain what is the so-called accumulator, and I can show you visually what that looks like. You have this, classic Plonk Sudoku. You have the initial state, this chosen part of the scheme, it's a property of the scheme, and if this bit is set to 1, then it's the case that we have to take this accumulator, this initial accumulator, and add it to the whatever value is there, and we get this value. And if it's the case that this is 0, then we don't really add anything, we just copy it over, right? And so this way we only add points that are described by our bit list. And you can imagine that this set, this XY, is a list of the validators that we're interested in. And so we have a commitment to that list. So, yeah, we get into more technical parts about the spec. In the original paper that Web3 Foundation researchers presented, they were actually using the 377 761 cycle. It's the case that these cycles actually have a highly two-adic structure in their field, which allows you to use the classic radix 2 FFT. We all know and love the radix 2 FFT. But if you factor the outer curve for the 381 curve, which is 767, you get these very, very ugly big primes, not very friendly to my radix 2 FFT. So we have to switch gears and use a different kind of FFT algorithm. So it's the case that the radix2 FFT is a special case of the Cooley-2K FFT. And the Cooley-2K FFT is just a way for you to sort of decompose. It's a kind of matrix factorization. You can decompose a DFT into two smaller DFTs if the DFT itself is of a composite size. And then if you can reapply this recursively, then you get back your radix2, which gives you a 2 log n complexity. But it's also the case that it can be combined with other FFT algorithms. For instance, we have Radar's algorithm, which is useful for DFTs of prime length. But there's also other fun stuff like Winograd, Good Thomas. If you're interested, it's fun stuff. All right, so let's get to the meat of zkCasper. It's the case that we need to initialize the verifier with a commitment to all of the validators in the validator registry. You can think of it, it's a classic light client. You need to initialize the state of the light client, and then you can just continually update from there. And also, we initialize the verifier with a bit list of all of the disabled validators in that commitment. So it's the case that some validators may have exited, they may have been slashed, whatever. So we let the verifier know that these validators are now inactive. So the prover provides what's the signature, the already aggregated public key of each attestation committee, and the attestation message for all of the attestation committees. And of course, a bit list that says which of the public keys in the registry were participating in this aggregate public keys. And then this APK proof that I just described that attests to the validity of those public keys. So the verifier performs this very weird thing there. That's a logical XOR. And what that does is if the prover had enabled some of our disabled validators, then that operation would remove them from the bit list that they supplied. And then we just take a sum of all of the APKs that were provided to us and verify them with the APK proof SNARK. If it's the case that the prover had indeed enabled some disabled validators, then that SNARK would no longer verify. If it's the case that any of those APKs are not in our commitment, that SNARK would no longer verify. So I leave the soundness analysis for the SNARK to Alistair and his talk. And now we can just do signature verification, right? So now we no longer know the individual public keys of the validators, but we're still able to verify the authenticity of those aggregate public keys. Right. Just going to quickly run through this one. So how does the verifier learn of validator set changes? Because, of course, the set isn't static. Validators join the set, they leave the set, what have you. Well, the attestations themselves contain what are these LMD votes, which the validators are attesting to what is the latest block in the chain. And the verifier can just use this latest block with Merkle proofs that I described earlier of the validator registry to add, remove, update their bit list basically of what they think is the disabled set of validators. And you can see that just through this homomorphic addition here. And I give a proof for that. It's a very short proof. Yeah. So safety and accountability. The verifier now has sort of zero knowledge of the set, but there's still safety through the preservation of slashable data. If it's the case that the verifier is presented with an attestation message that violates the Casper FFG protocol, then maybe if they did that on chain, then someone else could see that happen on chain and then report them back to Ethereum and then get them slashed. And the bit list also preserves accountability because we know what the individual public keys that were part of that sort of equivocation for the attestation. And of course, we uphold safety with the ability to report these slashable offenses. If you want extended reading, I write about this more on our blog as well. So what are the applications of this? First, you can have fully trust-free bridges to Ethereum with the highest cryptoeconomic security. It's basically you're running a beacon chain node like Prism, Lighthouse, whatever. It's literally running on chain, and you have the best security possible. Off-chain light clients could also benefit from this. I know there's Helios by the A16Z team. You can imagine the sync committee could also perform eclipse attacks on off-chain light clients in this way, in the same way they're able to eclipse on-chain light clients. So this prevents that from happening in the first place. You could also possibly run this in the browser. You can imagine you participate in the P2P swarm, but you just receive very succinct proofs of the attestation, so you're not doing all this multiple pairings and having to maintain the full set locally. Yeah, that's the end of my talk. I'll take any questions.
All right, thanks a lot. So we can take maybe one question while the next speaker, Manoush, is already setting up. Any questions?
Thank you for having me.
Yeah, thanks a lot.